Okay, gotta get going. Plenty of things to learn. Today we're going to continue to review the semester, although obviously can't do entire semester just in 1 or 2 days. We will probably have a review session sometime next week to get ready for the final. Okay, so disclosure thing. If you haven't learned this by now, then you're probably going to fail. Where did we leave off on Tuesday? Well, we were telling the somewhat revisionist history of quantitative analysis up to Fisher, basically. And pre-computer frequentists like Fisher were focused on the empirical challenges they faced at that time, which was analyzing and come up with some at least internally coherent way of estimating stuff for researchers. And particularly in the case of Fisher, this was largely experimental research rather than observational research, where you could make, some sort of a rationalization for your inferences, even when you have a small amount of data by today's standards. And so Fisher's great insight was basically to hitch the entire maximum likelihood wagon onto sufficient statistics. Because if you could put the distribution in an exponential family form, figure out what the natural parameterization is, figure out what the statistics, sufficient statistics are, add that up over your n observations, divide by n, and now you just have the sample mean of these sufficient statistics. And sample means, according to the central limit theorem, as long as there is a finite variance, are eventually going to converge such that your maximum likelihood estimates are going to have a multivariate normal sampling distribution, because the sufficient statistics that you set your estimating equations equal to have a normal sampling distribution across data sets. So if you collect data, estimate, collect data, estimate, collect data, estimate, those point estimates over a large number of data sets, research applications, are going to have a normal distribution. And this actually resembles a normal distribution pretty well, even for small to moderate n, provided the data generating process is not too skewed. And so we saw last time we have this equation, G prime eta over G prime, there's a -1 in there, equals the average sample sufficient statistic. And if the right-hand side converges to a multivariate normal distribution, so must the left-hand side. And your maximum likelihood estimates are just transformations, rotations, shifting, etc., of these multivariate normal. But it can't be emphasized enough that the problems people were facing 100 years ago and the solutions, such as they were to those problems, are not necessarily going to be the optimal solutions to the problem you're facing today. And today, we really face the opposite set of problems. So back in the day, 20 observations, they would estimate the mean of the population, whatever. Social scientists today estimating much more complicated models. So like regression and hierarchy and like mixtures and all this. But moreover, the main problem that a lot of people are facing today is that their n is too large. And that's just completely the opposite problem that Fisher was really worried about. Nowadays, how are we going to model a data set with 20 million observations instead of 20? And 20 million isn't even all that much by today's standards. But if you have 20 million observations, usually or invariably observational observations. And you're studying people as opposed to Fisher, who is studying biology. There's going to be a lot of heterogeneity in that data generating process, and your model has to capture that heterogeneity. And today's solution for today's problem is basically hierarchical modeling. The Bayesian version of hierarchical modeling makes a lot more sense than the frequentist version of hierarchical modeling that came along much later. And so basically, you know, it's not really Bayes' rule that defines who is and who isn't a Bayesian, because even frequentists accept that Bayes' rule is true if all the probabilities on the right-hand side are derived from an infinite number of repetitions. But what makes someone Bayesian, what makes Laplace Bayesian, and you know subsequent people, is using probability as a language to describe uncertainty, and using it to describe all forms of uncertainty in basically the same probability units. And so we talked at one point along the line that there are 4 sources of uncertainty that you have to worry about when doing a research project. The first could be called model uncertainty. Which models should be used? That has a lot to do with theory, but we learned stuff like Liu information criterion that could help you with that. There is parameter uncertainty. Within each of the reasonable models, there's going to be parameters. You don't know exactly what those are, and so you have uncertainty about those that you want to describe with probability. And for that, we talked about credible intervals, and we talked about being able to get the uncertainty of everything just by calculating the function and then calculating the standard deviation or the interquartile range or whatever it is that you want to describe your uncertainty about that thing can and should be done with the MCMC output. The third has different names. One paper that I think was particularly good calls this systemic uncertainty, or maybe systematic uncertainty. I don't know. But it's basically saying, well, what framework should you use to make conclusions? And so in the Bayesian framework, it ties, like we talked about, pretty directly into a theory of how to make rational decisions. With the frequentist thing, there is sort of the frequentist framework, but it's torturous to try to use that to make decisions that have some external reasonable to this. You can do stuff that's kind of internally consistent, but it doesn't seem to have a whole lot of real world applicability. But there's a lot of things out there these days that sort of de-emphasize probability in general, whether that's Bayesian or frequentist, and then you don't really know, or there's no obvious connection between the results you obtain and the decision to make in response to those results if you don't have probability as a bridge to get you from the results to the decision. And fourth is software uncertainty. Does the software do what it's advertised to do? Does it do what it intends to do? And this was a problem for Bayesian analysis for a long, long time, over 200 years, and that there really was no software that we could use to do Bayesian analysis and capture the first 3 parts of uncertainty with probability. That started to change in the 1990s when mostly Gibbs samplers were used, but we subsequently found that for any finite number of iterations, unless you're doing a really simple model, a Gibbs sampler might not give you a very good estimate, or the estimate it would give you if you literally ran for an infinite number of iterations. And when you think about this, the problem of trying to draw from a posterior distribution is just so much, particularly a big multidimensional distribution. It's so much harder than trying to do it in one dimension or trying to find the optimum of some surface. You have this sort of real numbers in k dimensions, And you can chop that k-dimensional space up into like little tiny arbitrarily small regions, and you need your Markov chain to visit each of those regions with a corresponding posterior probability. And you have to, do it in such a way that it's not like, the first 10,000 observations, it's over here, and that sort of gives you like a biased result, to the left, and then the next 10,000, it's over here, and that kind of balances things out. If you happen to stop after 20,000, you might get the average of that being pretty close to what would happen if you could do it analytically, or you could do an infinite number of MC/MC chains. But what if you stop after 10,000? You've only gotten draws from over here. And so you take the average of those, and that's a really biased estimate of the posterior expectation you're trying to obtain. And so it's not really sufficient for a Markov chain to be like tacking back and forth such that its expectation is the right answer, because you have to be really lucky to stop it at the right point where the posterior expectation is approximated by the mean of your MC/MC draws. You really need it to get to the expectation and stay closely to it as it continues to run, and then you can stop it after any finite number of iterations, and you get a pretty good answer. And so that is sort of the technological innovation of Hamiltonian Monte Carlo no U-turn sampling, the variations of no U-turn sampling that we've added over the years to Stan. Mitigates, but does not eliminate, a lot of the software uncertainty. But in principle, you could estimate any differentiable posterior distribution with Stan. And in practice, the vast majority of those, you can obtain a good answer, but it doesn't mean you can necessarily obtain a good answer with the parameterization that you have to write, that you write down. You may have to reparameterize things a little bit. You may have to put in more realistic priors than what you would like to do, etc. But for a lot of differentiable models, we can draw from the posterior distribution pretty well. And if we can do that, we can quantify our uncertainty in parts 1, 2, and 3 with those draws. And so, before Stan, there was not that many, but there were a few classes, different universities in Bayesian analysis or whatever, but you could go through the whole class and at the end not really get anything that's workable for the class of problems that you're trying to deal with. And so hopefully that shouldn't be the case anymore. So we talked about Fisher and the frequentist and stuff like that. But nowadays, certainly outside of statistics, a lot more attention is being paid to so-called supervised learning, machine learning, data mining, sorts of things that come more out of computer science, engineering, etc. And most of these, like almost all of these supervised learning approaches, choose some point estimate theta to minimize the sum of two functions. One is a misfit function between the so-called training data and the model, the predictions produced by the model. And this is actually, these misfit functions are usually just -1 multiplied by some log likelihood, Gaussian log likelihood in the case of continuous outcomes, Bernoulli log likelihood in the case of binary outcomes, etc. But some sort of misfit function that quantifies the difference between the training data and the predictions the model is producing. And then the second term of this function being minimized is a penalty function that's usually going to take the form of some distance between the point estimate and 0, the origin. And these penalty functions are also usually going to be the negative of some logarithm of a PDF. And so they can be interpreted like a prior. And so if you minimize the sum of those two things, and the first piece is the negative of a log likelihood, and the other piece is the negative of a log PDF, then the resulting theta hat that you get out as your point estimate can be interpreted as the posterior mode for some choice of likelihood and some choice of prior. And so when this happens, and it happens a lot, or something approximately like it happens a lot, it basically means the people who are doing these supervised learning things are implicitly defining a posterior distribution and then finding the mode of that posterior distribution, taking that mode theta hat to be the point estimate and throwing away all uncertainty. So you can really see a lot of supervised learning approaches is systematically ignoring all uncertainty. They talk a lot about, well, you know, you estimate it on the training and then you predict in the testing, and that gives you a way to choose, you know, is model 1 or model 2 better? But there's no way in that framework of quantifying, you know, what's the probability that model 1 is better than model 2? How sure are you that model 1 is better than model 2? They would say something like, well, I'm absolutely sure for this data set and this way of splitting it into training and testing that model 1 does better than model 2. What's the uncertainty? But if you ask, okay, well, you know, if you got more data tomorrow, how sure are you that model 1 is going to be better than model 2 for tomorrow's data? No way of answering that question within the supervised learning framework because they've de-emphasized the probability backing Bayes rule. Parameter uncertainty, you ask one of these lasso engineers, how certain are you that the parameter is theta hat? They tell you, I don't even know what theta hat is. I didn't look at it. I just generated the predictions from it. So how am I supposed to tell you how sure I am about something I don't even know what it is? Even if they did know what it is, they can't get standard errors for stuff like that. And even if they could get standard errors, that's answering a question that they don't want to answer either, which is, you know, what's the distribution of the estimator if you were to do this over and over and over again? That's the frequentist question. We have a frequentist answer to that, for better or for worse. Systematic uncertainty. Okay, random forest, you get, you know, these implicit parameters, you get predictions from it. You can, you know, predict better for this data set for, you know, one model than the other. How do you make a decision about what to do? Like, do you raise your prices or, you know, advertise more? Do you, you know, open up a new store somewhere? You know, what conclusions do you make about political race or something like that? There's really, it doesn't, the answers that come out of a supervised learning thing are insufficient to get you to, okay, this is how I'm going to make action. So, you know, you can predict this thing, you know, okay. But in order to sort of decide what to do in response to that, you have to consider like the costs and the benefits and what is, you know, the decision that maximizes expected utility or minimizes loss. And all the supervised learning thing people have is a point prediction that's optimal with respect to this sort of mathematically defined function. It doesn't speak to, you know, costs and benefits and uncertainty and risk aversion and things like that that have to be considered when making any sort of an important decision. Whereas with the Bayesian approach, yeah, we're getting this posterior distribution that's characterized by the same likelihood function and the same prior, but we get this whole distribution and we can plug this whole distribution into our cost function, into our benefit function. We can say, okay, if we're risk averse, we can quantify the uncertainty for this, and we can take into account that risk in our cost process, and we can come up with a rational decision based on the evidence that we have, the beliefs that we had coming into it, as to what would be the decision that maximizes our utility. But basically, supervised learning is just sort of anti-uncertainty. Yeah.
Are there like optimization frameworks that are Bayesian?
You can characterize the posterior distribution as a solution to an optimization problem. It's, however, an optimal function, whereas most of what supervised learning, OR, engineering, all that stuff is finding an optimal point. So you can characterize the posterior distribution as the closest distribution to the prior distribution that's consistent with the data, loosely speaking. So you can make that more precise. But basically, like if here's your prior distribution, your posterior distribution is or posterior PDF is the function that's closest to your prior subject to a constraint imposed by the data. So you can think about the posterior distribution as an optimal function, but that is way more abstract than what most people are doing when they're doing optimization problems, seeking the optimal numbers rather than optimal function. Yes?
So in a supervised learning context, the optimization is over an error surface on some minimum, right? So in the Bayesian context, would it be wrong to think about it as like there's uncertainty in the shape of that error surface, or?
Well, no, conditional on the data. We'll see this in a second.
Yeah.
You know what that shape is.
Yeah.
It's just you have to say, okay, this is a function. I have a bunch of draws from the function rather than I have one point that's not even a random draw. It's like systematically finding the optimum thing. And then there's sort of a question that's not really answerable within the supervised learning framework. Well, what function should we use to score different models? And from a Bayesian perspective, there actually is a deductive answer to that, which is the expected log predictive density. And we can do that, and that tells us the model that's expected to predict future data best, conditional on the past data. So we have a pretty well-defined solution to the model comparison problem, whereas with supervised learning, you could say, okay, this model is best with respect to this scoring function. This model is best with respect to this other scoring function. Which scoring function should we use? No real systematic way of doing that. So in response to the question, I think one of the best ways to understand this is to consider a model, and has to be simplified. So this is like a Logit model, not very many data points. There's no intercept, one predictor. We just have one coefficient to estimate. And we can see this in terms of different curves. So if you take the frequentist approach for these data set that I randomly generated, we get a likelihood function with respect to beta that looks like this. And you can just see visually, or your computer can tell you exactly what number that corresponds to. It's like 1.8. So that is the maximum likelihood estimator. That is the value of beta such that the data set we have is the most likely data set to obtain if beta was actually 1.8. That's very different from saying the most likely value of beta is 1.8. That's not correct. From a supervised learning perspective, they will often use lasso penalization function, L1 penalization function, that involves the absolute value of the coefficient. And so insofar as that is not 0, you get a penalty. Now, when lasso people do this, everything's upside down because they're minimizing rather than maximizing, but that's just scaling by -1. And so the penalty function is at its minimum when the parameter is 0. There's no penalization at all in that case. But if it departs from 0 in either direction, you have this penalization that's like linear in log. So this is what that L1 penalty function looks like if you flip it upside down. And so from a supervised learning perspective, the posterior, or the function being, let's call it maximized, they're actually going to minimize -1 times this, is the blue curve here. The sum of log likelihood with the Bernoulli case and log L1 penalization function. And so you get this surface, the blue curve here, which is the, something proportional. This is actually normalized, but something proportional. It has the same shape as this posterior kernel. But instead of saying, okay, I did lasso and I get this entire blue thing here, you say I did lasso and I find the optimum of it, and the optimum is 0. So the solution to penalized Logit model with L1 regularization in this case is 0. And so then supervised learning people act or go with the estimate, this is 0, 0.00000, repeating. But they've just, defined implicitly, oftentimes without knowing it, but some of them actually do know it, a posterior kernel. And, the Bayesian, you sort of look at the solution not as this one point that's the maximum likelihood estimator, not at this one point, which is the solution to lasso regularized Logit problem, but the solution is the entire posterior distribution in blue here. And it is true that the posterior mode is 0.0000. But Bayesians are not going to take that one point or any one point as being the answer. The blue curve here, just it integrates to 1. I've normalized it in this case. You can do that numerically in 1 dimension pretty easily. Describes our beliefs, inclusive of our uncertainty, about this coefficient. And our uncertainty is pretty considerable in this case because we don't have a lot of data. But, the posterior median is probably somewhere around 1. The posterior mean is going to be a little bit greater than 1. There's probably like a 2/3 chance that the coefficient is positive, and maybe a 1/3 chance that the coefficient is negative. Anyway, that's all just describing the distribution whose PDF is the blue curve. And so, whereas for frequentist, the answer is a single point, the maximum likelihood estimator. And for supervised learning, it's also a single point. It's just a different single point. But neither of those 2 points are particularly special in the context of an entire posterior distribution. And when you're, describing your beliefs, they have to be with respect to this entire curve rather than any 2 points. And that's a much harder thing to obtain, particularly in multi-dimensions. You can't calculate the denominator of Bayes rules, so you can't just do like numerical integration to normalize this. So we get a bunch of draws, but we can describe the posterior distribution arbitrarily well with, an arbitrarily large number of not too dependent draws whose distribution has the blue curve as its PDF. And so, the vast majority of people, if they're older, they're doing, maximum likelihood. If they're younger, they're doing lasso. But neither one of those are really a complete answer to any of the questions that somebody would be asking in a situation like this. But complete answers can be obtained just by doing manipulations of the posterior distribution. All right. Questions about that? The relationship between frequentist point estimation, supervised learning point estimation, sort of, and Bayesian trying to obtain a posterior distribution conditional on the data. So, with the frequentist approach, yes, you get one maximum likelihood estimate here. And if you drew another n observations and did the thing again, you would get a maximum likelihood estimate that was maybe a little bit different from that. And so if you do it over and over again, you get this distribution of point estimates, but except in like limiting circumstances that are accelerated with sufficient statistics and stuff like that, that's going to be a different distribution. I mean, conceptually, it's always a different distribution. The sampling distribution is a different thing than the posterior distribution, but it's not too hard to come up with scenarios in which, numerically speaking, that's a much different distribution than the posterior distribution. So it's numerically different in addition to being conceptually different. Whereas with the supervised learning thing, they don't really have any distributions to begin with. And so it's a very thin answer, like thin as in 1 point on the entire real line answer. This question. Questions? All right. So the R code, if you want to make that figure yourself, it was a little bit artificial because I used a sample size of 9. But if you have a lot of predictors and you do lasso, it's entirely possible that the posterior mode on some of those is going to be 0. And people who like supervised learning think that's a good thing. It tells me this coefficient is exactly 0. I don't need it in my model. Like, I gave the thing all these variables and it told me I only needed like 7 of them because it made the rest of them 0. And it didn't make the rest of them 0. You just ignored the uncertainty about the rest of them. Not the same thing. So there's lots of situations in the social science where maximum likelihood supervised learning really just can't do anything constructive or get going. And one of those, 2 of those, although they're very common, is situations where the data are missing, otherwise measured with error. Hierarchical models is another one. What you typically see, I mean, we saw already, there's sort of very weird hierarchical models from a frequentist perspective, from a supervised learning perspective. The most typical thing to do is just do 1 lasso per group. But there's not really a notion of partial pooling. That requires probability. And the Bayesian solution in these cases is the same as the Bayesian solution in every case. Treat the mismeasured or missing data as unknowns, condition on whatever observed data you have, update your beliefs about all the unknowns, inclusive of like the missing data, the true data that was mismeasured, the parameters, all that. You have a joint posterior distribution for all those things, conditional on the observed data that we can draw from. So in the case where data is missing not at random or not missing at random, that's going to entail specifying a model for the R array. Remember, R is this 2-dimensional array that's equal to 1 if the original data point is observed and equal to 0 if the original data point is not. So in the missing not at random case, that's going to entail specifying a model for R using the completed data matrix X. And then a lot of people ask, well, how do I do that? And it's, equivalent to the question, how do you model any binary outcome? So we just have to see R as being an outcome of this data generating process. So part of the data generating process is whether you as the researcher get to observe the data that was generated, or for that data point, it's missing. So one simplistic model for R would just say Rij is Bernoulli likelihood. The probability is a logistic CDF of eta. Eta, or eta I, is equal to the ith row of the completed data matrix. So XC, X completed, is, we saw last week, we stitched together the observed data and proposals for the missing data into this matrix that, we know what observations were originally missing and which were originally observed from R. So we stitch that X completed matrix together. We take the ith row, we multiply by a matrix of coefficients beta, we get predictions eta. We transform eta, which is the log odds, to the probability scale. And now we have a Logit model for whether the ij data point is observed or not as a function of xc. And xc is going to contain both originally observed data, which doesn't change, and proposals for the missing values, which do change on every MCMC iteration. So we have some coefficients beta there. We're going to need a prior. We could just do standard normal for those. That's not necessarily that realistic. So we might want to scale up those coefficients by some unknown standard deviation that we can put like an exponential prior on. These last two lines imply that beta times sigma is distributed normal with mean 0 and standard deviation sigma. So this is just a hierarchical model where we're estimating how much the coefficients on XC vary from question to question, the columns of the R matrix. So we can estimate that too. There's lots of ways to estimate what effectively boils down to a Logit model for the columns of R. But you have to do this all simultaneous, or at least that's the best way to do it. There's multiple imputation algorithms that try to do things in 2 stages, but they're pretty much unable to allow the data generating process to be missing not at random. They have to assume it's missing at random, in which case R doesn't provide any additional information about the missing values that we're estimating. By specifying this, where eta is a function of xc, xc is a function of xo and xm, and R is observed, we're getting additional information, additional precision about the missing values from this piece of the likelihood, in addition to the information that came from like the multivariate normal likelihood stuff that we specified for the complete data likelihood last week. So you just need to piece together a model for XC with a model for R given XC. Not that hard, but way beyond what most people in the social sciences do, which is either only analyze the rows of X such that the row of R is all ones, or maybe they do multiple imputation assuming that the stuff is like multivariate normal but missing at random, which is a very strong assumption to make. But there's a weird phenomenon. It definitely happens in the social sciences, but I think it happens elsewhere, where the less people know, the stronger assumptions they make. So you're like, is this data generating process missing at random or missing not at random? I don't know. I have no idea. So I'll just make the strongest possible assumption that it's missing at random, instead of making specifying a more general model where missing at random is like a special case of the more generalized thing. So if all these betas are 0, or if sigma is 0, which is pretty much equivalent, then the probability of you being observed or missing actually doesn't depend on XC. So now we're in missing completely at random world, or maybe there's an intercept in there. You can put an intercept in X if you want. You probably should. Anyway, there's a special case of this where like all the betas are 0, and now we're not missing at random. But in general, not missing at random is a much more reasonable assumption to make than this sort of special case where it actually doesn't depend on the unobserved X's. Same thing with like, there's posts on Piazza about it. Like, okay, I'm estimating a hierarchical model. What should I put as my prior for the correlation between the intercept and the slope? I don't know. If you really have no idea the correct answer to that question, like what prior should you put on the correlation, is uniform between -1 and 1. So if you really mean, I have no idea, there's a perfectly good solution that describes your beliefs, uniform between -1 and 1. If we're just estimating one correlation, it gets more complicated if we have a whole correlation matrix. We got to satisfy the positive definiteness constraint. But even in that case, you have a perfectly good solution if your beliefs are, I have no idea, which is LKJ with the shape parameter of 1. That is uniform over correlation matrix values of size k. But let's just say you have one correlation to estimate. So the corresponding prior, if you really have no idea, is uniform between -1 and 1. But that's not what people tend to do. What they tend to do is assume it's exactly 0, 0.0000 repeating. So rather than specifying some prior distribution that's uniform or has a mean, median, mode, etc. of 0, but has some variance around it, they just say, well, I'll assume it's exactly 0. And there's just a real disconnect. Like, that makes no sense. But that's what you see a lot, and the only way to really understand that is, you know, the people who are doing this just really don't know that much about probability distributions, don't have the capability of describing what they actually believe in terms of probability distributions, even though there is, you know, a very coherent connection between, you know, what it is they actually believe and some probability distributions that would be consistent with what they believe, as opposed to doing something that is much stronger than what they actually believe. Okay, so missing data. Questions about that? Questions about how to relax missing at random model R along with X? Okay. So how would we do that in terms of stand code? Actually, even easier than writing it out in terms of math. So inside the, you know, there was a whole loop from I equals 1 to I equals n where we put together x sub c, and x sub c is a row vector, or array of row vectors that is the union of xo and xm for that observation. And then, okay, you know, you do all that. And then for the ith observation, you just do target plus equal Bernoulli Logit LPMF. And then what is the log odds for person I? It's just the X completed data for person I multiplied by beta multiplied by sigma. And so you do that for each person. Now you've modeled the R's. So R bracket I comma is all J elements in the R matrix for row I. So those are conditionally independent given XC and some matrix beta. And then outside the loop from I equals 1 to n, you need to put the priors on beta and the prior on sigma, which is, again, just use the distributions, put underscore LPDF after it. And then it's, you know, just expressing your beliefs about those things before seeing the data. So it takes like 3 additional lines to get rid of the missing at random assumption. And the wherewithal to actually do it. Question? So what if the missingness is not conditionally independent? The missingness on one question is not conditionally independent from the missingness on some other question, J prime, even given the log odds for all those, which is another way of saying it. If I told you that Rij is 0, does that predict missingness on Rij prime, even if I told you, or even for 2 people that have the same eta? It's entirely plausible. Often, if you sort of look at this, you'll see like missingness comes in spells. So somebody will just skip like 5 questions in a row. stuff like that. So it's sort of, I mean, it's more ridiculous to try to defend the assumption that things are missing at random, but it is also a little bit difficult to defend an assumption that things are missing not at random, but everything's conditionally independent given the completed data. And so as I was posting on Piazza last week, these two people in 2009 derived a distribution which they were using as a likelihood for spatially correlated binary outcome variables. So they had a lot of data on like exercise or time use or something among teenagers, but there was sort of entirely plausible spatial pattern to that, in that people who live near each other or people who are friends are more likely to have the same ones or zeros on their outcome because in some space they were close together. But you could also use something like this. You could use this in a variety of ways, but you could use something like this when considering the location of variable j in your data set and trying to model the R's. So is it the case that there's some spatial association between the 12th column of R and the 13th column of R? Is there some reason why missingness or observability on those tends to go together? That's not really conceptually different from saying, do people in the zip code 12 have some spatial association with people in zip code 13? And for those of you who are in the QMSS but not graduating, or those of you who are not in the QMSS offers a class on GIS and spatial modeling. It's not overtly Bayesian, but you can do Bayesian things with spatial data. And so if your spatial data in this case are binary, you can use the distribution that's defined in the Bhat and Sener paper, which they show as this. You pretty much have a regular Logit thing going on here, and then multiplied by 1 plus the double sum of this over all these terms, where theta captures the spatial dependence between variable q and variable k. So if all these thetas are exactly 0, then you just have 0 multiplied by all this. All that sums to 0, and then you have just your regular Logit model times 1. And you're back to the case where things are conditionally independent. But if those thetas are not exactly 0, then estimating a Logit model that assumes they are doesn't give you the right estimates of like the betas and the sigmas and the other parameters that go into the main part of that model. So we asked on Piazza, you have to put the constraint that this thing doesn't exceed or isn't less than -1, so that this remains a valid probability mass function. And I talked on Piazza how to enforce that constraint. Basically gave up to the model block for a STAN program like this, and then how would we write down the model block if we wanted to use this distribution for the likelihood of some bunch of binary outcome variables. You've got to be able to go from math to code. I mean, yes, you should estimate this thing with a Bayesian estimator, but this really has nothing to do with Bayesian. Like, this is just the likelihood part of it. It's a component of a Bayesian analysis, but this is just a likelihood. It really doesn't have anything to do with the STAN language. Like, could you write that likelihood down in R or Python? What do you have to start with? What's the first step?
Take the log.
But yeah, so if you're doing this in Stan or your maximum likelihood or whatever, you're actually going to want the logarithm of this likelihood function. But the only thing that really simplifies when you do the log is this product becomes a sum. The logarithm of this piece in brackets here, there's no real simplification to it because some of the terms can be negative. Like the overall thing can't be less than -1, but the pieces. So there's not actually a whole lot of simplification there. You just have to put that whole thing in brackets inside the log function. Calculate eta first. Good. So that'd be like the first line of a Stan program. Okay. So if we get eta, how would we do, this first piece here?
Would that be these log x something?
You could do some log, some x business on this. Yes, on that term you could. That would make it more numerically stable, which is good because more difficult models like this, you run into more numerical instability problems, separation, all kinds of stuff like that. So yeah, that would be good.
The inverse Logit function. Eta to the inverse Logit function.
Yeah. So you could go from log odds to odds to probability. But actually, if it's going to be the log likelihood, then you need the log of the probability. Okay. Could probably handle that. How would we go about dealing with this second term here in brackets?
Double for loop. For
Yeah.
A and for Q.
2 for loops, right? This is just going to be either -1 or 1, so you could implement that with if else, depending on whether dq is equal to dk. So d here is the outcome variable. That's a weird convention on transportation researchers. They don't call their outcomes like y or anything civilized like that. And then how will we deal with the pieces that we're summing up here?
I need to choose 2 etas, one for the first one, Q, and one for the K.
Yeah.
And then that would be indexed by the for loop variables. You sample theta QK.
And not in Stan, but I mean, yeah, we're building up a likelihood, and it's going to draw from the joint distribution of everything.
So that theta is also indexed by for loop variables. And then for the second and the exponential, you just take the Logit function that is for those data on those for loop variables.
Yeah. I mean, there's additional details to it, but that's basically the idea of it. But you got to be able to do stuff like this if you're going to implement slightly more advanced models than the things people were doing in the 1970s, and they were just doing regular Logit model, ignoring all the spatial association. And this, I think, underscores. So I did put some code for that here. That all this stuff about frequentist estimators, maximum likelihood estimators, they have all these properties. They're consistent. They're not affected by transformations. They achieve the Cramer-Rao lower bound. They're asymptotically multivariate normal. All this stuff, actual applied researchers don't care about at all. The main first criterion in most applied researcher data scientist mind is there code already out there to do it, so that I don't have to write the code for it, which is ridiculous for science. Like, it's just completely unacceptable for a PhD student or for someone in the QMSS program. I mean, you know, other business contexts, maybe that's about as good as you can do. But it just, for science, it's not only like counterproductive for science, but it's just cowardly that people would rather use, it's a combination of laziness and cowardice. It's one, like, I don't want to write the code to do this, but two, like, if I use somebody else's code and that code is actually wrong, it's not my fault. It's the person who wrote the code's fault. So, like, you know, my article still gets published. It gives the wrong answers, but it's somebody else's fault that it gave the wrong answers. So I'm not gonna like lose my job or anything over that. But it's not the way to do science. So you have to be able to, you know, write your own code to implement new stuff. But, you know, a lot of people don't want to do that, and they would rather use a likelihood function that doesn't really match on to what they think the data generating process is, if that likelihood function is already implemented, preferably in, you know, Stata or SAS or whatever. So you can just sort of click your way to the answer. But that's, you know, not as much of a mindset in like computer science and stuff like that. They're more comfortable saying, okay, like, here's a problem. And rather than spending like half an hour searching the internet for like code that's already implemented this thing, I'll just write it out myself and it'd be shorter. But, you know, those are for people who are sort of naturally comfortable with, you know, writing down code. And you have to achieve that level of comfort, even if you're not, you know, a political scientist or, you know, data scientist or whatever. It doesn't particularly matter at a conceptual level whether you do that in the Stan language or, you know, some other language. The Stan language is more or less optimized for expressing stuff with probability distributions. But the Stan language isn't really harder than any other computer language, and in some ways it's easier. But the idea of, okay, I'm going to write down this posterior kernel, is still, you know, hard for a lot of people. Even though the posterior kernel is just like, most of the lines here are just for the likelihood, which conceptually you would need to do, or somebody would need to do, in order to do frequentist inference on this. Or somebody would need to do it if you did lasso penalization. Like, you have to write down all this stuff. And then, you know, usually when we write Stan programs, we're just like, insert priors here, because your priors may be different from mine. So I'm not going to hard code that in it. But, you know, there's like 2 more lines to express your priors on the unknown parameters, but all the hard stuff, such as it were, is here. So you've got to practice going from math to code. Writing down a likelihood, write down the priors. Now you have a posterior kernel, but more importantly, you have a model. And then, you know, conditional on some data, you can update your beliefs about the parameters in that model. But, you know, really to do quantitative social science, you have to be able to write down in code models for how you think these data that you're about to collect, or maybe that you already collected, but these data were generated. You know, okay, there's a lot of things where we think it might be generated according to this type of process, including of ours. Questions? All right. So hierarchical models, just really goes back to the multiplication rule. If we have 3 variables, A, B, and C, we can write their joint distribution of A, B, and C as like marginal times conditional, or we could have marginal involving A and B and conditional of C given A and B, or we can write this as marginal A, conditional of B given A, conditional of C given A and B. All of those expressions are equivalent to some joint distribution of A, B, and C. But in this expression, are A, B, and C parameters, or are they data? For Fisher, it's a critical distinction because parameters are fixed and data are random. You can estimate parameters, but your estimator, because it's a function of data, is also going to be a random variable. For Bayesians, this distinction is really kind of optional. And if you saw that video by Richard McElreath, he really tries to de-emphasize this distinction in favor of the thing, well, you have beliefs about the data generating process for all the variables, A, B, and C. I don't like that as much because, you know, even for Bayesians, I mean, Richard's a little bit hesitant to say this as a biologist, but, you know, a lot of people of the Bayesian view say, okay, you know, these parameters are constants, but my beliefs about them follow a probability distribution. And in that sense, it's sort of the same as my beliefs about observed variable. But basically, if you can write down a data generating process involving nodes A, B, and C, then it's not super important which of those you call data and which one you call parameters. And so we saw several instances of this. Like in the case of bowling, A could be that gamma parameter that governs the shape of the probabilities that come out of those Fibonacci type functions. B could be what happens on the first roll. C could be what happens on the second roll, given what happens on the first roll. And this gamma thing, which kind of captures your skill as a bowler or differentiates the skill between or among really good bowlers. With like the homework assignment we did on car racing, A could be sigma, which is the standard deviation of the intercepts across drivers. B is the driver-specific intercept that has a normal 0 sigma prior on it. And C is the outcome. Does driver D win or lose that race? And so you can do frequentist estimation of hierarchical models, but for frequentist, you have to do integration to integrate out any of these B things if they're not data. Of course, if you're integrating them out, they're not really parameters either, because they're no longer considered fixed constants, but rather things that are random due to the design of the experiment, even though frequentists sort of push that to sort of very observational data, but whatever. To do maximum likelihood estimation, you have to get a likelihood function that's free of B. So you have to do an integral and then choose A to maximize that likelihood once B is gone. But in addition to just being very weird, what if you're interested in B? For the Bayesian thing, you just get the joint distribution of A and B, conditional on C. And if you're interested in B, like, what's the probability that this and that person is the best driver that year? You know, you can compute that. If you integrate B out, you can't really make inferences about it anymore. It's gone. All you can make is statements about like how much variability there is from one driver to the next in NASCAR, rather than making probabilistic statements about a particular driver. So Bayesian approach to hierarchical model is really way better. Just came along a few years after the frequentist approach, more than a few years. So RST and RMBMS both more than capable of estimating hierarchical models. Moreover, if you have minimal familiarity with R, such that you can use LM or GLM, you ought to be able to use stan LM, stan GLM. All you have to do is specify the priors, although the defaults work pretty well. And then you have to interpret the results in a Bayesian fashion, which is a lot easier than trying to interpret the results from GLM in a frequentist fashion. Remember, if you don't have an informative prior on the coefficients, it's usually best to specify the non-default argument QR equal true. That will reduce the software uncertainty, make it easier for Stan to draw efficiently from these posterior distributions, less likely to get stuck if you have two parameters that are really highly correlated, etc. Extending from that, if you can use the glimmer function in the LME4 package or the GAM4 function in the GAM4 package, you ought to be able to use Stan underscore glimmer, Stan underscore GAM4. You're going to have to specify the hierarchical structure in addition to what you specify for Stan GLM. In the case of GAM4, you also have to specify which variables are related to the outcome or the linear or the predictor through a nonlinear smooth spline function deal. But that's just relatively small step. The BRM function and the BRMS package can estimate models that are very similar or the same as all of these, plus a lot more because it generates Stan code on the fly and compiles it, whereas the RStanArm package comes with handwritten models that are compiled. But eventually you'll find yourself in a situation in which you want to do a model not merely for a homework problem that isn't already supported by RStanArm, BRMS, a few other packages. So there's no such thing currently as Stan underscore Logit, but you need to be able in RStan, in the Stan language, to write down a Stan program that is sort of equivalent to modeling, who wins given the person's starting position and intercept that, or this should have been like name here. An intercept that varies by driver. And you need to be able to doing that model yourself in RStan. It's basically a Logit model with the restriction that somebody has to win and everybody else has to lose. So the outcomes are not conditionally independent of each other. Yes?
Sorry, what's the -1 mean?
Means no common intercept. Because that would be unidentified. Talked about before. So post estimation, RStanArm and BRMS are pretty harmonized. There's the same or similar functions to do all this stuff that you should be doing, particularly involving posterior predict, whether that's for checking or whether that's for interpretation. A lot of people fail to appreciate how awesome the posterior predictive distribution is, because there is no posterior predictive distribution in the frequentist land or in supervised learning. But there is with Bayesian. This is the conditional distribution of future data given past data. You can write it down as an integral that you can't solve, or you can do it in practice by drawing from the posterior distribution of theta given past data, and then using that realization of theta to draw y tilde from the same distribution that you chose for the likelihood when you did your Stan model. That gives you predictions for future data or predictions for the data you already have, whatever. And so you can do all your inference in terms of observables, y tilde and x, and you don't have to be talking about log odds or, anything like that. That really is just speaking a foreign language to a lot of people, inclusive of people who consider themselves to be pretty quantitatively savvy. So there's really no reason to interpret coefficients when you can just interpret the relationship among observables implied by your model. Finally, I think this was mentioned maybe on Piazza, but just in case so you have an example of it here, you can use the BRMS package to get started on a Stan program that you then might go in and tweak. So they have an example of this, estimating some Poisson model with some shifting of the intercepts and stuff like this, and kind of a medical example. So let's say you just kind of wanted to start as this as your base, and then maybe tweak it to do something that BRMS can't do currently. There's a make_Stan code function that you can pass to all that, and there's a make underscore stand data function, which will give you a named list of stuff where the names correspond to the names that are declared in the data block of the stand program that's generated by make stand code. And so you can look at this list. It's got like N and K and Y and X and a bunch of other things corresponding to the hierarchical structure in your priors. Those are all going to get passed to the data block of the stand program that is generated by the BRMS package. This stand code is considerably more readable than the stand code in rstand-arm, and it has comments and stuff telling you what things are, but basically, you have N and K and X, the sort of thing we have in almost any regression model, and then we have Z1 and Z2, which are these intercept shift indicators that are, vectors. They could be ones, etc. There's this stuff in the transform data where the variables are centered. That tends to make stand work better, less dependence between the intercept and the other things. Then you have the parameters declared, in the parameters block and what they all mean. And then, if you wanted to, you could write your own model block that goes on after this. Of course, the stand code that's generated comes with a model block, so it would really just be editing this. Like I said, this code is not necessarily the most optimal, and it may be not exactly what you want, but it ought to be something that compiles, and it ought to be like a good blueprint to start from. So we have, priors, we have likelihoods, they contribute together. This is using the tilde syntax, which is pretty much equivalent to the target plus equal, but it drops constants, slightly more efficient, slightly less useful after the fact. And then there's a generated quantities block where they shift the temporary intercept over by the vector product of the means of X and the coefficients in order to get an intercept that refers to the original uncentered X rather than the centered X that it was using in the model block of the stand program. And so you need to be able to use BRMS, but if you can use BRMS, you can get code, and then you can just sort of make tweaks at the margin to make it go faster, or to make it do more what you want to do, to maybe change the priors or something like that, to do to draw from the posterior distribution that corresponds to the distribution implied by your actual initial beliefs and the data that you're about to collect. All right. So that's all I got. I will put this up on Courseworks tonight, and I will post on Piazza as soon as we have a time and a date for the review session. Presumably it'll be in the basement of IAB again, but we might try to get like a bigger room like this one, and so maybe more people can fit. And in that case, we might have kind of like a longer single review session as opposed to two short ones. But we'll have to see about room availability and stuff like that. All right? There.
Yesterday.